The multivariate normal describes a distribution of points in a multidimensional space, for instance a k-dimensional space. For this, we need to define the following parameters. We need a mean vector mu, which is also a k-dimensional vector, and a covariance matrix sigma, which defines the interactions between dimensions as well as the variances in each of the dimensions. It is a k by k dimensional matrix. If we now count the number of parameters that are involved here, then we see, well, we need k parameters for the mu, and we need k times k, so we need k squared in the sigma. However, since our sigma matrix is symmetric positive definite, this will boil down to be just k times k plus 1 in brackets. But even with this simplification, this one scales quadratically in k. So if you now think of, for instance, k being way greater than 1,000 dimensions, you need to save a lot of parameters. Can we reduce the footprint of the multivariate normal? And indeed we can. In this video, we will introduce 3 different ways of defining a multivariate normal distribution. Hi and welcome to this new video. The 3 ways of defining a multivariate normal that we want to look at in this video are first by full covariance, which is just the classical way you might have seen before. It will be a repetition. Then the second is a diagonal covariance. So we don't have any off-diagonal terms anymore, or in other words, we don't have any correlation between the dimensions anymore. And lastly, a spherical, or also called isotropical Gaussian, in which case we have only one variance or standard deviation for all of the dimensions. For this video, we will actively switch between the handwritten notes and the Python session in order to show the different ways in TensorFlow probability. Let us start with the very first, the full covariance. For the full covariance, as the name says, we define the entire covariance matrix. So with all of its k squared term, but of course we only need to save the k times k plus 1 terms, as we have the symmetry property. So if we know the upper diagonal elements, we don't have to save the lower diagonal ones. And contrary to the others, this allows for the definition of interactions between the dimensions. And these interactions are also called correlations and basically allow us to rotate our Gaussian distribution to not be just x-aligned. So let me also note this down. This is also referred to as correlation if we look at standardized data. In TensorFlow probability, you might have already seen this before. The way to implement this is by the multivariate normal tri-L, which means triangular lower matrix. And we get this by performing the Cholesky decomposition on the sigma matrix. So that's what we will do first. Perform a Cholesky decomposition. And this Cholesky decomposition can also be thought of as the square root of the matrix. And if you recall, the square root of a variance in a one-dimensional space is the standard deviation. So this is just a multi-dimensional analogon of the standard deviation. So it works as following. We have the sigma matrix and it is decomposed into a lower diagonal matrix times the same matrix transpose. And also recall that this checks for symmetric positive definiteness. So also checks for SPD. That's a handy thing, so we don't have to take care of it. If the Cholesky decomposition does not work, then our matrix is not symmetrically positive definite. And I see there's a typo, it should be called decomposition. And if we then have the decomposition, we can create the random variable with the mu and the L matrix. And as you've also seen here, all the 3 ways that we will be using to define the multivariate normal always require the full definition of the mu vector, as there is no way to save on this one. The only aspect here is that we shrink down our covariance matrix. I'm now in the interactive Python session. I loaded the TensorFlow modules as well as Matplotlib so that we can visualize the different distributions. I already set it up in interactive mode and created a figure that we will have always on top here to judge on the distribution of points that we will draw from our distributions. So let's start with the full covariance definition. For this, we will use TensorFlow probability.distributions.multivariate normal and then tri-L. And we feed it with first a location vector and I want it to be centered at 2 and 2, and the scale triangular lower matrix, for which we have to use tf.linalg.heureski in order to perform the Heureski decomposition, and I want this matrix to have a variance of 2 in the x direction, a covariance of 1 between the x and the y dimension, and then of course we need a 1 here in order to be symmetric, and I have like a 3.0 variance in the y dimension. Then let's close this down, and we have our random variable x full. We can create a data set full by sampling the distribution, let's say 500 times, and then we can scatter this by using the dataset full and scattering the 0th dimension, and then scattering the first dimension corresponding to x and y. And then we see here, first it is obviously centered at 2 and 2, and then we see the little bit greater variance in the y dimension, so the second dimension here. And on the x-axis, probably like 2, it's not too easily visible. But what is definitely clear is that we have the covariance. So if you were to draw contour lines, then you would see that these contour lines are rotated in a sense, so they are not axis aligned. And that's what we can do with our full covariance definition. Next up, we have the diagonal covariance, for which we just define the variance basically, and no covariances between the dimension. So our sigma matrix is the diagonal matrix created from a variance vector basically. So this is a collection of the variances in every dimension. So let me note this down. This is the vector of variances. And just to give you some perspective here, if we have the covariance matrix, then recall it was a k by k dimensional matrix. And on the diagonal elements, we now have a sigma 0 squared, a sigma 1 squared, a sigma 2 squared, and so on and so forth. And we have zeros on the off-diagonal elements, so no covariances. And then obviously our vector of variances will be the vector that is given as a sigma 0 squared, sigma 1 squared, all the way to sigma k minus 1 squared. And it is a k-dimensional vector. Let's see how this affects our definition of the multivariate normal. If we look at the covariance matrix, we see that it appears in two places. First, in the exponent, where it is inverted, and then we also have to take the determinant of the covariance matrix. So let's look at these terms individually. We have the determinant of the covariance matrix. And we know the determinant is also defined as the product of the eigenvalues. So we go from k0 to k minus 1 over the k eigenvalue of our covariance matrix. Now also let me note this down. This is the product of eigenvalues. And the neat property of this diagonal matrix is that the eigenvalues of it are on the diagonal. So sigma 0 squared is an eigenvalue, sigma 1 squared is an eigenvalue, and so on and so forth. So in essence, this is equal to taking the product over the variances. So it's from k0 to capital K minus 1 over sigma k squared. So it's basically just taking the product over this vector. And for reference, let us also note this down. The eigenvalues are the diagonal entries of the diagonal matrix. And with this, we simplified our multivariate normal by quite a bit. Next up, we have to look at the inverse of this matrix. But the good fact is that the inverse of a diagonal matrix is a diagonal matrix with each of the diagonal elements inverted, or in this case, just the inverse of all of them. So basically this means 1 over sigma 0 squared, 1 over sigma 1 squared. So that means that sigma inverse is then just 1 over sigma 0 squared, 1 over sigma 1 squared, and so on and so forth. And we still have zeros in the off-diagonal elements. Putting everything together, basically get the normal over x under the mu vector, and the covariance being defined as the diagonal matrix based on the covariance vector. And in this case, we get that it is 1 over the big square root of the product from k0 to k minus 1 over sigma k squared multiplied with 2 pi raised to the power of k, and then times the exponential of minus 1 over 2 of x minus mu in brackets transpose And then we have the sigma 0 squared, sigma 1 squared, or basically 1 over it, all the way to the k variance or k minus 1 variance. And then here we also have the x minus mu, and then closing brackets for the exponential here. And this also, of course, simplifies the multiplication that has to happen within the exponent, greatly reducing the computational effort, in particular in high dimensions. Well, how does it look in TensorFlow probability? Here again, we don't define it by variances, but by standard deviations. So it is called multivariate diagonal, but it uses the scale diagonal. Or in other words, it is using a standard deviation per dimension. So a standard deviation per dimension instead of the variance. So instead of variance. And of course, we can easily calculate this by saying that the standard deviation vector is just a component-wise square root of the variance vector. Or we can also just call it the diagonal elements of our Cholesky vector, or the square root of our covariance matrix. Returning back to our interactive Python session, we have to find an x diagonal as tfp.distributions.multivariate normal diagonal, and we have to create a location, and I want to center it, let's say, at -2 and 0, because we have some space here. And then we have our scale diagonal. And here I wanted to have a standard deviation of 1 in the x direction and let's say 4 in the y direction. Okay, let's close this down, and we can create a data set diagonal by sampling our diagonal random variable again 500 times. Then let's also scatter this into our chart here. And here we see, obviously, it has a way higher standard deviation in y than in x. It is approximately centered at -2 and 0, but more importantly, it is axis aligned. So again, see, we can't use any correlation here. We see it's definitely axis aligned, so the main axes of the ellipsoid contour lines are aligned with the x-axis and the y-axis. Then we finally arrive at the spherical or isotropical. And if you're doing something that is related to mechanics, for instance, then isotropy is quite an important property there, which just means that the properties of a material are independent of the direction. And here we could also think of it. And I also think that spherical is a nice word, because we will see that this in higher dimensions creates a sphere, or like the contour lines are spheres. And the idea is, as it's probably obvious, that we have one variance or also standard deviation for all of the dimensions. So more precisely, this would mean that the covariance matrix is sigma squared, and it's just a scalar, no index, multiplied with the identity matrix. And for the Cholesky factor, we then have the standard deviation multiplied with the identity matrix. So here you see, this is just like the multivariate analogon of the standard deviation. And then if we go back up, we see that the determinant is the product of the eigenvalues. And the eigenvalues of a matrix, which is of k by k and has only sigma squared on the diagonal, is just sigma squared multiplied with itself k times. So we have that the determinant of our covariance matrix is the product from k0 to capital K minus 1 over sigma squared. But since there is no index here, we are just multiplying it k times with itself, as said. This is as if we would raise it to the power of k, and this is basically the same as 2 times k. And how about the inverse? It's even more simpler here, because the inverse of the covariance matrix will be sigma squared times the identity matrix in brackets inverted, and this is basically just 1 over sigma squared times the identity, because the identity is also the inverse of the identity. And then plugging it into our definition, we get that the normal distribution over x under mu and the sigma squared identity covariance matrix equals to 1 over the square root of sigma raised to the power of 2k times 2 pi raised to the power of k, multiplied with the exponential of -1 over 2 sigma squared of x minus mu in brackets transpose times x minus mu. And I didn't write the identity here because it would just like not change the scalar product that is apparent here. And also it reminds me of the univariate normal here. But really important, the difference is that our sigma is also raised not just to the power of 2, but to the power of 2k, and also the 2 pi as a normalization constant. So let me note this down here. This is just a regular scalar product. So a regular scalar product. Now again, the question, how is it defined in TensorFlow probability? And here I want to show you 3 different ways. And the more obvious would be to use the multivariate diagonal, which also has the option for a parameter, which is just the one scalar quantity that is valid for all dimensions. And it's called with diagonal scale multiplier. We will see about this in a second. Then the second way is to also use the multivariate diagonal object and use it with the sigma times tf dot ones of k in order to create a k-dimensional vector which just has sigmas on it. We call this again for the standard deviations. And lastly, I also want to show you something else, which is by the help of the independent distribution of a batched normal distribution. Then let's define the x spherical as tfp.distributions.multivariate normal diagonal. And let's, for instance, put it down here. So let's center it at 5 and minus 5. So 5.0 and minus 5.0. And then there is the option for a scale identity multiplier. And here I will choose a 1.0, a unit variance, a unit standard deviation, or even unit precision for all of the dimensions. Then we can create a data set for the spherical Gaussian by sampling our spherical object 500 times. And then we can scatter this one too. So let's put it here and also here. And then we see we get our object that is spherical. I mean, in 2D, a sphere is the circle, but you see that the contour lines are definitely circles. It is centered at the 5 and minus 5. And of course, if I would change the identity multiplier to 2, then it would be more wider spread here. Let's do this with the next. So let's do it an x spherical 2. And for this, we use again the multivariate normal diagonal and provide it with the location. And now maybe down here. So add a minus 7.5 and a minus 5. And then let's do a scale diagonal. And here I will use 2.0 times tf.ones. And here I need to do 2 because we are in a 2-dimensional case. And then we can create the dataset spherical 2 by sampling our spherical 2 object 500 times. Then let's scatter it and let's hope for it. Yep. And here we go. You see it's centered at this point and it's wider spread out than the green points. It's quite obvious. And again, we have this spherical or isotropical property that it is having circles or in higher dimension spheres as contour lines. And then coming to the last, I want to define it by the help of a batched normal distribution. So for this, I will use x spherical 3. And for this, I will use tfp.distributions.normal. And note the difference. Here we have multivariate normal, and here we have normal, which indicates univariate normal. And if I now provide it with a multidimensional entry for the location, it is creating a batched normal distribution. And I want to fix it at minus 7.5 and 5.0. And I will provide it with a scale of 1.0. Of course, this is then valid, or this is broadcasted against this, so it will also be 2-dimensional. And the big difference is now, if I look at spherical 2, I see it's the one from here, the multivariate normal diagonal. It has no batch shape and an event shape of 2. So it is a 2-dimensional distribution, but we only have one of it at the same time. Whereas if I look at the spherical 3, I have an event shape of 0, or like a scalar event shape, and the batch shape of 2, because I'm evaluating 2 univariate normals at the same time. And if I were to sample this one and then plot, this would actually work. I mean, in this case, we can interchangeably use batch and event dimensions. However, it is nicer, especially if we want to query probabilities and so on, to have a perfect match of the dimensionalities, so I can move the batch dimensions into an event dimension by the help of the independent distribution. And for this I will override the spherical free with the tfp.distributions.independent of x spherical free. And then there is the flag of reinterpreted batch n dimensions, and we have to set it to 1 in order to then go down to the scalar batch case that we have only one distribution evaluated at the same time, but this one then has an event shape of 2. So if we look at it again, then we see event shape of 2. Well then, long story short, let's create the dataset spherical free by sampling the spherical free 500 times. And then also let's plot it here, just put it in here. Let's see what kind of color it gets. And there we go. We have it again here that it is centered at the point that we desired it to be. And it has almost the shape that we expected with the circular ISO contours. With this, I'm at the end of the video. If you enjoyed it, then please leave a like and subscribe to this channel. If you have any questions left, then write a comment. I would be happy to answer it. Here you will now see similar videos. And with this, I hope to see you next time.